In this video, we study a different type of estimation method, and it's the maximum likelihood estimation. This is really a dominant method in statistical estimation. So I really want all of you to understand at least how to apply this method, at a relatively basic level. More complicated questions, they are complex in the density and how are you going to solve it. But the principal idea is still the same. That's why this video is rather important, not just for this course, but also for many future applications. So let's begin with density or probability function, or even the mixed. So x can be continuous, can be discrete, can be mixed. That doesn't matter, okay? It's parametric, so its value depends on theta. Theta does not need to be a single parameter. Can be a vector of parameters, so it can be more than one to be estimated. Okay, we write down the so-called the likelihood function. So here what we have is actually the complete model. We know the observation. So here we know the values of the observation. So xi are the those xi's are the i's observations. Now what we do is, this is obviously either the density or the probability function, right? Because we assume IID. Because of independency, we times them together. Because they are identical, we apply the same function. So that's where we apply the IID assumption. This is the likelihood. In other words, you can think this as a joint distribution, right? If you think of that, we can actually generalize. We might be able to drop those IID assumptions if you are able to come up with the joint distribution directly. Then all we need to do is directly plug in everything. Of course, that's more complicated to handle. We don't do that, but it's certainly a possibility of doing it that way. So here we consider the IID, so we simply times them together. Now what would be the purpose? So on the left-hand side, we treat L, big L, as a function of theta. So this is a function of parameters, unknown parameters, right? So nevertheless, those are constants. Those thetas are constants. So the left-hand side will be a function of theta. This bold X denotes the vector of observations, something we have already observed. Since we observe this particular sample, we should hope for this to be relatively big, right? Because we have observed this, right? So our intuition is we should pick, or we should select those theta such that this is maximized. So our goal is to maximize the likelihood of seeing this particular sample, right? Because in reality, this is what we see. Since we have already observed that, we should go backwards to maximize the chance of observing this particular sample, right? That is the principal idea behind maximum likelihood estimation. That is to build a model, try to maximize the likelihood of seeing a particular sample or a particular observations. And then that's it. That's what we are trying to do, right? In most applications, it's actually convenient to take log to get to the log likelihood. Once you apply log, the product becomes summation. And in actuarial science, we often apply distributions that are within the so-called exponential family. So there are kind of exponential functions involved. And once you take logarithm for exponential, it greatly reduces the difficulty of analyzing it, right? So that's why taking log is convenient. And once we take log, it's often we use little l or small l to denote So big L is for the likelihood, small l is for the log likelihood. Those two are equivalent because log function is an increasing function. So maximizing big L is the same as maximizing small l in the sense that the solution will be the same. The solution of theta will be the same. Okay. In the textbook, there are some asymptotic results. I will not go through those, but I actually want you to know at least the first you need to know Fisher information because this is related to the variance estimator. So it's nothing but the expectation of the second derivative, right? And here, once you take log, it's logrified and it's for a single one, right? So we get this is the so-called the Fisher information for the. This is for the likelihood, right? This is for the single observation. This is usually what we need. A very important result is not here. It's actually this theorem. It tells us when n goes to infinity, what kind of distribution you would expect on the maximum likelihood estimator, right? So theta hat is the solution that maximizes either the log likelihood or the likelihood. So the same solution, right? This is nice because we know that when n goes to infinity, it follows this normal distribution, right? So in other words, once you pick a sample, you can figure out this theta hat, right? And we can construct a 95% confidence interval or 99% confidence interval for the true parameter theta, right? It's easy to do. So that's why this theorem is very helpful, okay? But I don't test you this, SOA might. So it's still good to know this result. Okay, to us, those are not that important. We just need to know how to apply it. So we begin with the easiest scenario. That's when we have complete individual data. So in other words, we know everything. We know the values of all observations, and there are no truncation, no censoring. We want to calculate the MLE of those parameters. Okay, so now let's, of course, the first thing you do is to write down either the density or the probability function, depending on whether it's continuous or discrete. So the first one is a Poisson distribution. So let's write it. Right, this is the probability function, right? So let's take log. It will be negative lambda plus x times log lambda minus log x factorial. So theta, not theta, lambda is the parameter we're trying to maximize, right? So we need to sum up, right? Because once you apply log, we do summation. When you sum up, obviously you get negative n times lambda is this term. And when you sum up, this is I, right? So it will be log lambda times the summation from 1 to n xi. Okay, in most of the time, we want to use a shorthanded notation, right? The right-hand side summation obviously equals n times the sample mean. This is how sample mean is defined, right? So that's the first term. The last term, it doesn't matter, it's a constant. It has nothing to do with your parameter. So you can just write it as a constant, if you want. We are trying to maximize, right? The tool we have is obviously the first order condition. So we differentiate with respect to the parameter, right? So we get this very easy equation, equate this to 0. The solution is the MLE. So MLE is the solution to the maximization problem. You are trying to maximize. So you are trying to maximize over all lambda. So lambda should be positive in this case. So obviously our lambda, since it's equal to the sample mean, obviously it's positive, right? And we actually notice this is the same as the estimator obtained from the moments matching, right? By the way, this is a necessary condition, right? Not exactly sufficient. What you need to do is to differentiate again to get the second derivative, and it will be n x bar divided by lambda square. Everything's positive, so this is negative, right? So you have to actually have a concave function like this. So your first order condition does give the unique maximizer, right? So here we can claim this is indeed the maximizer instead of the minimizer, because if your second derivative is positive, the function is convex. Your first order condition actually gives you the minimum, right? So I would suggest you to check just to make sure you do get the correct result. Okay. The second one is geometric, right? I'm sure you can easily write down the log likelihood, and then we differentiate with respect to the parameter, right? Here it's theta, so we differentiate, we get this equation. Once you solve this, you will be able to get the MLE, right? The third one is a continuous, follows exponential distribution. It's actually very easy to handle for the exponential, right? So once you write this down, the next step, here they skipped some step, right? So this is the PDF of exponential. Let's take a log. It will be log lambda minus lambda times x, right? And my small l will be the summation from 1 to n log f xi at theta. So now I have n times log l minus, let's take out this lambda, summation from 1 to n xi. As already mentioned, I always write the summation as n times x bar. So by the way, this is how they get this step, right? So in your exercise or in the exam, give me the full details. Don't write me this in the first step. It's not a good practice. You should write it step by step. From there, we differentiate, right? This is easy to do, right? It's a simple calculus question. Okay, then we have a special case I actually want to mention. This is a uniform, okay? The distribution is uniform 0 to theta. So we know the density is 1 over theta, right? It has nothing to do with your observation value, right? So no matter what you observe, the density is always 1 over theta. And since they are independent, so it will be 1 over theta raised to the power of n. So that is the likelihood function, right? So if you optimize, well, what would be theta? Theta is 0, right? When theta is 0, is infinity, right? Obviously, that shouldn't be the case, right? In all the previous ABC, well, when we solve for the optimizer, we solve it in the global sense, right? It's unrestricted, right? But here, we actually have restrictions. Your theta cannot be anything. We have already observed n observations going from x1 to xn. And since it follows a uniform distribution, so all of them must be between 0 and theta. So since theta is greater than any observation, theta should be greater than the maximum, right? So there is actually a lower bound on x, on theta. Theta should be at least as big as the maximum observation. It cannot be smaller than that. Otherwise, you have issue. It's not a uniform, right? So since we have a lower limit, and we know in this particular form, the smaller the theta, the bigger the likelihood. So you will choose the smallest theta you can possibly pick, which is the maximum value of your observation. So this is a very, very good and rather special example to somehow put a little emphasize or little attention to the domain of your parameter. Sometimes it really, really matters. So the domain of your parameter is really important, right? In the previous ones, we actually didn't mention, but of course, there are some assumptions. For instance, when you study Poisson, lambda should be positive, right? When you study this theta should be actually between 0 and 1. This should be greater than 0. This should be greater than 0, right? And this obviously is greater than the maximum of all observations. So they are domains. You need to pay attention. For instance, here is sample mean. Sample mean is always positive, so there's no issue. And then we get this theta, right? And well, obviously this is between 0 and 1. That's why I didn't talk about whether it's possible or not, right? 1 divided by something bigger than 1, so it's less than 1. Sample mean is positive, so the ratio is also positive, right? So you need to actually think about that. Of course, this is also greater than 0. So in the future, once you get MLE, take a quick second to think whether this is feasible. Right? In optimization, we call this whether this is a feasible solution, right? Within the possible range. Okay, uniform is a nice example. Then we do some asymptotic. I leave that to you. I don't want to do it here. And then we do grouped and the incomplete. Nothing is special for them, right? Previously, we have each observation. We know xi, then we plug in f at xi. Now we don't know. We know we have some observations, let's say between C1 and C2. We don't know exactly the values, but we know they are between C1 and C2. We know how to compute this, right? This would be the CDF at C2 minus the CDF at C1, right? And then if they are independent, then if I have, let's say, N1 observations between C1 and C2, what would be the probability? CDF at C2 minus CDF at C1, and then I raise to the power of N1 because they are independent, right? So likelihood is talking about possibility or probability, right? So if you don't know exactly the observation, we do the best we can, right? The best we can is we know we have n observations in this interval, and we know what is the probability for each one to be located between C1 and C2, right? If there are n of them, we just raise to the power of n, that's it. That's how we deal with group data. This is what I just mentioned, right? This is how we deal with group data, and then we multiply them together for all the groups, right? Of course, we should also take logarithm to help us simplify. This is the first case. Sometimes we might have censoring, right? So let's say there's a limit, okay? So let's say I have k observations that are, well, at least as greater than u. Let's say we apply a policy limit of 100. I have, let's say, 10 observations that are at 100. Maybe they are exactly at, but more likely they are because of censoring, right? Let's say I have a ground loss of 200, but if there is a policy limit of 100, it will be counted as 100, right? So again, this is partial information, but I simply do this, right? I have k observations that are greater than u, and I know the probability for the random variable to be greater than u is simply 1 minus the CDF at u, right? Or the survival function at u. Then there are k of them. By assuming independency, I just raise the power to k, right? That's it. And I can also do mixed. I can have some observations. I know the value. Some of the observations I only know they are greater than something, right? So we can also do mixed if you want, right? That's not difficult to do. So, and sometimes we can also do a deductible, like conditioning on x greater than d. Well, you just need to divide by the conditional probability, right? So in summary, what we do under the maximum likelihood is to study the probability. right? It goes to probability. And then since they are always independent, we times the probabilities together for all of them. Then we try to maximize this likelihood, which will be a function of the parameters. So that's what we do. There are a lot of theoretical work. Here we have a few more, right? Block one. Actually, I don't want to do any of them. I actually want to use two specific SOA questions from the textbook. I think those are better examples. I will solve them to give you a better idea when you have somehow more complex case. So in 12.41, losses are assumed to follow an inverse exponential distribution. I can't write it in nice form, so let me write it again. Okay, it's very easy to verify this is a CDF. So first of all, it's increasing, right? 1 over theta is decreasing, then I put a negative, so it's increasing. Exponential is increasing. When theta goes to 0, is e to negative infinity is 0, right? When theta goes to infinity is 0, so e of 0 is 1, right? So it increases from 0 to 1 and is continuous. Obviously, this is a CDF. So now let's differentiate to get the PDF. Okay, exponential will stay, and then for the term, when we differentiate, we get theta divided by x squared. So this is the PDF of inverse exponential distribution. We observe 3 losses with exact amount, and 7 of them are less than or equal to 60. So we have a mixed case, right? 3 of them, we know exactly the values. The other 7, we only know they are less than 60. Well, it doesn't matter. And also the question itself is interesting. In most cases, we want to get the MLE of theta, but here it's not. Calculate the MLE of the population mode. So what is mode? So mode is the x value such that the PDF or PF takes maximum. So basically x is the mode is the x value with the highest probability. So that is the first thing we need to do, right? How do we know when we get the highest probability? We need to maximize this, right? Over all x greater than 0. So in order to solve this, we need to differentiate, right? So let's differentiate with respect to x. The first becomes theta over the cubic times the exponential. And when I differentiate again, obviously, it gives me the same term. So first order condition, let's make it the 0. Okay, we're trying to solve this equation. There are many things we can cancel. This can be canceled, and one of the theta over x squared can be canceled. So I know this will be move the negative to the other hand side. 2 divided by x, right? So since x is positive, I can also cancel this. So mode equals theta divided by 2. So it's a function of theta. So eventually we want the MLE of theta over 2, right? So of course we're trying to get the MLE of theta first, and then it's done. The next thing we need to do is how are we going to handle this kind of incomplete data, right? So we know we have, for each of those, we have fxi, right? I equals 1, 2, 3. And for the rest 7, it will be f at 60, right? F at 60 is e to negative theta over 60. We have 7 of them. So now let's put them together. So here, if you want, you can do a little, well, you can apply log first. to see what it looks like, okay? So we will get log theta minus theta divided by xi minus log xi squared. This part has nothing to do with theta, so we don't care. So now, and also we can apply log to this. This is because we know it is less than or equal to 60. So when we apply log, this is, okay. So now let me write down the log likelihood. It will be 3 of them adding together. So it will be 3 log theta minus theta. The first one is 1 over 186. The second one is 91. The third one is 66. This part I actually don't care, so I can keep it. It does not affect my theta. And the last one, I have 7 of them. There is minus 7 theta divided by 60. Okay. Let me move this a little down so I can have more space. So now what I do is I need to differentiate. So let's differentiate this L with respect to theta. So 3 over theta minus the whole constant part here. And the third term has nothing to do with theta. The last term is, okay. By first order condition, I will make this equal to 0. By the way, from here, we easily see the small l is a concave function, right? Because when I differentiate, I get a negative value, obviously. So from here, we get 3 over theta equals this plus. So now I know my MLE will be 3 divided by 1 over 186 plus 1 over 91, 1 over 66 plus, right? So once I get theta hat, it's not done yet because eventually what I need is theta hat divided by 2 because this is the mode, right? Once you do the result, it will be 10.1226. So this is obviously not an easy question, right? It's a lot of work to do, but nevertheless, the analysis are straightforward, except there are many detailed work we need to pay attention. The first thing is you need to know the definition of mode. If you don't know mode, there's no way you can solve this, right? And you also need to be somehow familiar with calculus. In particular, knowing how to apply the first order condition to solve an optimization problem. This question is not that bad. It's just a group data. I want to show how you can solve when data are grouped. So first, let me rewrite the CDF. So we have 9 losses that are less than 10. So less than 10, so x is 10. There are 9 of them, so raised to the power of 9. There are 6 of them between this and this. So once I do subtraction, it would be theta over 10 minus theta over 25. I have 6 of them. Finally, I have 5 bigger than 25. So theta divided by 25 is 5. Okay, this is the big L. So now let's take log. So 9 times log 1 minus theta and plus, okay, I can factor out this theta. So my plus, well, if you want to do minus whatever you want, it's possible. Right? Obviously, you can simplify, but there's a constant, so it doesn't matter. Plus 5 times log theta minus 5 times log 25. Those are constants, so they do not affect anything. So now let's differentiate with respect to theta. So 9 states, this is a log, so I put it in the denominator, and by the chain rule, I have negative 1 over 10 plus 6 over theta plus 5 over theta. Let's equate the first derivative to 0. Again, you can see easily this is a concave function because all the theta at the bottom. So when you differentiate again, you will get negative value. Now let's move times 10 on both hand sides. Move to the right hand side. Left hand side will be 11 over theta. On the right hand side, I will get 9 divided by 10 minus theta. Okay, so do the cross multiplication. I get 110 minus 11 theta equals 9 theta. So 110 equals 20 theta. So theta hat would be 11 divided by 2, 5.5. So this is the MLE of theta, right? Sometimes, I can also ask you slightly different things, right? I can ask you some function of theta, right? For instance, I can ask you what would be the MLE of the population mean. So then you need to actually integrate to get the mean first, which will be a function of theta. And then the MLE of mean will be the function of this, right? So that's the study we do, right? There are many exercises from the textbook, and I actually would encourage you to try because as you can see, there are so many previous SOA questions in this topic. So it's almost for sure that in the future SOA STEM exam, you will see this type of questions. So let me end here for this video, and that also concludes this course.